Hey everyone, so in this video we're going to be talking about hypothesis testing, and this is going to be the first video on hypothesis testing. So a little bit about the motivation behind where hypothesis testing comes from. So remember, the whole goal of statistics is to use data to make decisions or conclusions about the population of interest. So we collect a sample, we summarize it in some way, and we make inferences about a population. And that's kind of like the big picture of statistics. If that idea wasn't in place, then statistics wouldn't even be a thing. So, a hypothesis is a proposed explanation for some phenomenon. And we like to objectively decide one way or another if the observations from our sample are significant enough to conclude whether or not a hypothesis is true. And this is what we call hypothesis testing. So just a quick example to show you what kind of questions hypothesis testing can answer. So let's say we're interested in whether or not a coin is fair, so we're just going to flip it 20 times and see what happens. So in the back of our minds, we know if the coin's fair, then we would expect roughly half of the flips to come up heads, and that would make sense. So let's say we flip the coin and 15 heads come up in the 20 flips. So now we have to ask ourselves, is the coin fair? Well, it's kind of difficult. It's like, of course, that's possible that we would get 15 heads and 20 flips, but is it so extreme of a result that we can conclude that the coin is not fair? And that's kind of hard to know just by eyeballing it. So we have to objectively decide one way or another if the coin is fair. So this is where hypothesis testing comes in. So the way we structure a hypothesis test is we're going to have two competing hypotheses here. We're going to have one that's called the null hypothesis, which we're going to denote by HO or H0. And then we're going to have an alternative hypothesis, which we're going to denote by HA, or sometimes it's referred to as H1. And what we're going to do is we're going to use what we have from our sample to essentially pick a side. But one thing we have to do here is we have to use one of them as our baseline, and we're going to use the null hypothesis as our baseline. So all of our decisions are going to be made based on the null hypothesis. So essentially what we're doing is we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Those are the only two conclusions that we can come to here, and that simplifies it a lot. So we don't make decisions that are centered around HA. We can't reject the alternative hypothesis, and we can't fail to reject the alternative hypothesis. And then the last thing we don't want to do is we don't want to accept the null hypothesis. We're going to assume that it's true for the sake of trying to disprove it, but just because we can't prove it to be wrong, that doesn't necessarily mean it's right. So we can't really accept the null hypothesis. So the null hypothesis is always going to be a statement of equality, and it's what we assume to be true until we have enough evidence to go against it. Now, again, we can't accept it because just because we can't prove it wrong, that doesn't necessarily mean that it's correct. But what we can do is try to find enough evidence against it to be able to reject it. Now, the null hypothesis is a statement of equality, and the alternative hypothesis is a statement of whatever we'd like to test. So, for example, for the coin flipping example, we had a null hypothesis of p being equal to 0.5. And how do I know that? Well, we assume that the coin is fair until we have enough evidence to go against it. And with a fair coin, p is going to be equal to 0.5. The probability of heads is going to be equal to 0.5. And our alternative hypothesis, that's what we're trying to prove, is that the coin is not fair. So if the coin is fair, then p is equal to zero point 0.5. So if the coin is unfair or not fair, then the probability of heads is going to be not equal to zero point 0.5. Whether it's less than or greater than, this is what we're trying to prove. And then the last thing to note here is that it doesn't necessarily have to be a not equal sign in the middle here for the alternative hypothesis. It kind of just depends on the context. We could claim that the probability of heads is greater than zero point 0.5, and we could test that instead. Our conclusions will be slightly different, but we can declare this as our alternative hypothesis just as easily, depending on the context. So now let's talk about test statistics. So a test statistic is a statistic that's used for hypothesis testing. It's a statistic that's used for testing. So test statistics are useful because they take everything we need to know to carry on with our hypothesis test and pack it into one value so that we can use that to calculate probabilities. So we're taking all of this data and just shoving it into one value, and that will help us determine whether we reject HO or fail to reject HO. So now we need to use probability because we need to calculate the probability that we observed data that was at least as extreme as what we saw. And that's what test statistics are for. So from the coin flipping example, we observed 15 heads and 20 flips, but is that extreme enough to be able to say that the coin is unfair? Is 15 extreme enough? So that's what a test statistic can help us calculate the probability of. So some examples of test statistics are z statistics and t statistics, which we've calculated before. So now we also have to talk about what's called the rejection region. So whenever we construct a hypothesis test, we have to determine how extreme the observations need to be for us to conclude that the null hypothesis should be rejected. So if our test statistic falls in the rejection region, then we reject the null hypothesis. And if our test statistic is not extreme enough to be in the rejection region, then we fail to reject the null hypothesis. And we'll look at an image of this in a little while. So in order to determine where the rejection region is, we first need to determine what the critical value is. And a critical value is what sets the threshold for the rejection region. And yes, this is the same kind of critical value from before. We're going to be finding it in the same way. So for a one-tailed test, which means HA is going to use a less than sign or a greater than sign, we're going to use Z alpha or Z1 minus alpha as our critical value for the test. And that's because our alpha level here, it's not going to be split up into two tails like when we were talking about confidence intervals. Our rejection region is going to be all on one side. And again, we'll see an image of this in a little while. So for a two-tailed test, when the alternative hypothesis uses a not equal to sign, we're going to use Z alpha half and Z1 minus alpha half as our critical values for the test. And this is the same logic as when we're constructing a confidence interval. Our alpha is going to be split up into two tails, a less than tail and a greater than tail. And those are going to be the critical values for setting our rejection region. So now let's talk about what are called p-values. So a p-value is formally defined as the probability under the null hypothesis of observing data as extreme or more extreme than what was observed. So in other words, the p-value is the probability of observing data that extreme or more extreme by random chance if the null hypothesis is actually true. So a low p-value actually is evidence against the null hypothesis. So if the null hypothesis is true, then we wouldn't have such a low probability of observing something so extreme. So a high p-value means we don't have much evidence against the null hypothesis, because observing that data is very plausible under the null hypothesis. So what we do is, before we carry out our hypothesis test, we define a threshold for which we would reject or fail to reject the null hypothesis based on what the p-value is. So this is called the significance level, and this is actually what alpha is. We've seen alpha before. Now, the most common value of alpha is going to be 0.05, but occasionally you'll see other type of alpha levels pop up. Sometimes you'll see zero point zero 0.01, sometimes in medicine you'll see 0.08, and then other times you'll see zero point 0.1, but usually what we see for alpha is typically 0.05. And the reason we call this a significance level is because anything beyond that value is what we're going to consider statistically significant. So, for example, if our alpha level is 0.05 and we observe a p-value that's less than 0.05, then we would reject the null hypothesis and declare that the result is statistically significant. So let's look at an example. So suppose we're interested in the average overnight temperature that people set their air conditioning to during the month of July, and we want to test the hypotheses here. So our null hypothesis is going to be that the mean temperature is 77 degrees, and the alternative hypothesis is that the mean temperature is less than 77 degrees, and we're going to use a significance level of 0.05. Now, let's say we gather data from 100 random households and find that the sample mean of overnight temperatures is 73.4 degrees. And let's say, for example, that we know the population standard deviation is 1.9 degrees, just to make this simple. Without doing any calculations, what do we think about the p-value? Do we think it's likely that if this is true, if the actual mean temperature that people set their air conditioning to overnight is 77 degrees, do we think it'd be really likely that we would come up with an average of 73.4 degrees from 100 people? Honestly, I don't think that's very likely. If this was actually true, we would think the mean would be pretty close to 77, and that looks like it's pretty far away. So let's actually do the calculation here. So since our population standard deviation sigma is known and our sample size is greater than 30, we can apply the central limit theorem and we can use z here. So remember, to calculate z, we just had to standardize our sample mean. And the way we do that is to subtract the hypothesized mean, which was 77, and then divide by sigma over the square root of n, just like we've done before. So this is going to be 73.4 minus 77 divided by 1.9 over the square root of 100. And what that'll give us is negative 3.6 over 0.19, which is negative 18.95. And remember, most of the z values are between negative 3 and 3. So for a z value to be negative 18.95, that's really extreme. It's so extreme that we can't even look it up on the table. The actual p-value here is the probability that z is less than negative 18.95, which is pretty much zero. So the low p-value, which is less than our significance level of 0.05, tells us that we can reject the null hypothesis in favor of the alternative hypothesis. That means we have enough evidence to suggest that the true mean overnight air conditioning temperature in July is less than 77 degrees. So tying everything together, Note that there's a relationship between the test statistic and the p-value, just like there's a relationship between the critical value and alpha, the significance level. So there are actually two equivalent methods that we can use to conduct a hypothesis test. So one way would be to determine the critical value or critical values, and if the test statistic is more extreme than the critical value or critical values, then we would reject HO because the test statistic would be in our rejection region. Otherwise, if the test statistic does not fall in the rejection region, then we would fail to reject HO. The other method, which gives you the exact same result, is to use the test statistic to calculate a p-value just like we just did. And if the p-value is less than alpha, then we reject HO. Otherwise, we're going to fail to reject HO. So let's look at another example. So let's say we're interested in testing the lifetime of XYZ brand's light bulbs. So typical LED bulbs last an average of around 30,000 hours with a standard deviation of 5,000 hours. So 36 light bulbs from XYZ are selected at random and then they're tested. The sample is found to have a mean lifetime of 31,124 hours, and we're going to assume the population standard deviation is 5,000 hours, which is the industry average. So, is there evidence to suggest that we should switch over to XYZ brand's light bulbs? So, in other words, is there evidence to suggest that the mean lifetime of XYZ's light bulbs is greater than the mean lifetime of the industry average? So, in other words, what we're saying is the industry has an average of 30,000 hours for their light bulbs, but the sample that we tested from XYZ has a mean of 31,124. So, what we could do is we can use hypothesis testing to tell us whether or not we should switch over to that brand of light bulbs. So, let's carry on with this test. So, as always, just like before, it's always helpful to list out the information that's given to us. So we have a hypothesized mean of 30,000. That's what we're going to test against. We have a population standard deviation of 5,000 because we assumed that it was going to be the industry average. And then we have a sample mean from XYZ's bulbs that was 31,124. And what we're testing here, again, this is based on the context of the problem. So this is about reading the problem and determining what we're interested in here. So the null hypothesis is going to be the statement of equality. We're going to assume that XYZ brand's light bulbs last an average of 30,000 hours because that's the industry average. And then what we're testing is whether or not we should switch over. We're testing whether or not XYZ's bulbs last longer than 30,000 hours. So we're going to go about solving this problem using both methods. So first, let's look at the critical value method. So since our significance level was 0.05, that's what we were told to use. And since it's a right-tailed test, our critical value is going to be Z alpha, which is 1.645. So that means if our test statistic is greater than 1.645 or more extreme than 1.645, then we would reject the null hypothesis. So the other thing to note here is that if this was a left-tailed test, if our alternative hypothesis was that mu was less than 30,000, then our critical value would just be negative 1.645 because it would be the other tail of the distribution, the negative side. So our test statistic here, again, we can use Z because we have a sample size greater than 30 and the population standard deviation is known. So when we determine Z, we'll find that Z is going to be 1.349. And since 1.349 is not as extreme as 1.645, our critical value, we would fail to reject the null hypothesis. So that means we don't have enough evidence at the 5% significance level, to suggest that XYZ's light bulbs last longer than other light bulbs from the industry. Now, notice we did not say that we accept the null hypothesis. Just because we couldn't prove that null hypothesis wrong, that doesn't necessarily mean that it's true. So all we can say here is that we failed to reject HO. So now let's do that same example using the p-value method. So remember when we calculated our test statistic, we came up with z equal to 1.349. And remember our significance level was 0.05, so that means if our p-value is less than 0.05, then we're going to reject the null hypothesis. So the p-value is going to be the probability that we observe as extreme or more extreme of a result if that null hypothesis was actually true. So the probability that we observe something that extreme or more extreme is going to be 0.0887. And that's greater than 0.05. So that means we fail to reject the null hypothesis, which we would expect because that's the result that we got from the critical value method. We're always going to get the same result for both methods. So here's an image of what's going on here, because I know it's a lot of information, but it might be helpful if we look at exactly what's going on here. So down here, we'll see that this is alpha. This is what's setting our rejection region. So our rejection region is going to have an area of alpha. The area in this tail is going to be our alpha level. So the area of this orange tail right here is going to be 0.05. And the z value that gives us an area to the right of 0.05 is 1.645. And that's our critical value. Now what we have in blue, this was our test statistic. This is how extreme the result was. If the result was more extreme, then it'd be more off to the right here. And the area to the right of this is going to be 0.0887. And calculating this area tells us how extreme this result is. Because if this test statistic was further to the right, then we'd have a lower area here, which would mean that our result is more extreme. And in fact, if this test statistic was to the right of this critical value right here, then it would fall somewhere over here, which would give us an area of less than 0.05, which would tell us that our p-value is less than 0.05 and we can reject the null hypothesis. So that's why these two methods are equivalent. It's because this and this are related, and this are related to each other. So no matter which method we use, we're going to get the exact same result. But that's essentially what's going on here. So anyway, that's it for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.